Hello, my name's Graham Coleman. I'm the Director of Student Engagement at St Isaac Newton Sixth Form in Norwich. Here's a 20-minute video to tell you all about Space Station, Moon and beyond, and to do some maths involved in that as well. Just a bit of background on me to begin with. I'm a regular maths teacher. I've been teaching maths and A-level maths for getting on for just over 20 years now. Here's a picture of me with one of my classes. The reason I know about space is because back in 2003, I went on a teacher training placement at the Kennedy Space Center in Florida for a week. Here's a picture of myself in front of launch pad 39. This is a launch pad from which Neil Armstrong and Buzz Aldrin took off from when they went to the moon. We also got to see the vehicle assembly building. The statistics on it are that each of those stars is the size of a person, so you could do a star jump inside one. Here's a picture of the Raffaello module of the International Space Station. This is now up on the space station. They used it back then for essentially carrying parts to and from the space station. This was a particularly exciting day because we found these gloves kicking around. These are moon gloves. That's pretty exciting. But we looked further and we noticed that these gloves had a date on them. I don't know if you can quite see that there, but it says June 1969 and the name Lovell. So we worked out that these are Jim Lovell's gloves and that these gloves would have flown around the moon on Apollo 13 in, I think it was about 1970. The only reason these gloves are here on Earth and I was able to try these on is because Apollo 13 didn't land on the moon. In 2005, I went to the Goddard Space Center. Here's one of the centrifuges that they've got there. This is a massive machine. They use this for testing spacecraft, just spinning around and getting used to those G-forces. And here I am getting very excited in front of the stereo spacecraft. These are two of the telescopes that they use to observe the sun. Again, this is back in 2005, I think it was, when I went on a visit to the Space Telescope Science Institute. Better known as the Hubble Space Telescope Control Room. So I'm going to tell you today about the International Space Station. So the International Space Station is the size of a football pitch, much like Harrow Road. It goes around the Earth. It just goes round and around the Earth in low Earth orbit. In order to stay up in space, going round Earth in low Earth orbit, it needs to go at 17,500 miles per hour or 28,000 kilometers an hour. That's how fast it has to go to stay up there. My first question to you today then, and when we get to it, I'm going to ask you to pause the video. There's a question by Chris Hadfield. So Chris Hadfield is the Canadian astronaut that took his guitar up to the International Space Station. And his question is...
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung-out cloth? So,
what is going to happen to that wrung-out cloth? Now, I know you can't answer. Usually, if you're with me, I'll ask for hands up. Common suggestions that I get is that the water sprays out everywhere, loads of little droplets in all different directions, because there is no down, because we're in space. Another response that we sometimes get is that the water hangs around the thing in a kind of round, big, bubbly blob. A third response that I sometimes get is that the water just kind of, like a big, big bubble, keeps on expanding outwards. So I'm going to zip forwards on the video a little bit, and we'll find out what happens to a wrung-out cloth.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet.
So you can see that the water stays there, hanging around the washcloth.
It's becoming a tube of water. The water's all over my hands, in fact. It wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is, the water squeezes out of the cloth, and then because of the surface tension of the water, it it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
So that surface tension that you saw there is the same thing that if you ever slightly overfilled a cup or a glass or a mug with water, then it's the same reason that that water tries its best to stay in the cup. It's the same reason that raindrops are spherical around. It's because the water does its very, very best to contain as much volume within the smallest surface area possible. And it brings us on to our first maths question. My question to you is this. What is the circumference of the Earth? I'll tell you 3 facts. The International Space Station orbits at an altitude of 250 miles high. So that is, it's 250 miles above the surface of the Earth. It travels at a speed of 17,500 miles an hour. And at that speed, it completes one orbit. Like, it goes all the way around every 90 minutes. I'm going to show you that diagram, or show you that information slightly differently. Pause the video. Can you have a go? The challenge is, what is the circumference of the Earth? Let's see what the answer is. The circumference of the orbit is the first thing you're going to work out. You're going to work out the circumference of that white arrow all the way around. So you're going to do 17,500 times 1.5. So every hour and a half, it goes 26,250 miles. However, that isn't the circumference of the Earth yet, because it's the circumference of that white arrow, which we can see is a bigger circle than the circle of the Earth. So from there, we can actually, because we've got circumference, we can work out the radius of the orbit. 26,250 divided by 2 pi, which gives us 4,177 miles. That radius there includes the 250 miles high that the space station is. So from that, we're going to subtract 250, and that's going to get us the radius of the Earth, 3,927. And from there, we just work it back upwards. 3,927 times 2 pi gives you 24,680 miles. And I've shown you also here is Google's answer. You can see that the numbers, they're not exact, but they're pretty close. I think they're within about 1% or something like that. Just with ballpark figures, rounded figures, it's not. The space station doesn't orbit 250 miles exactly. It doesn't go 17,500 miles exactly. And it doesn't take 90 minutes exactly. But even with those figures, we can work out things about the Earth. And we can be pretty accurate in it as well. So well done if you got that one. So Sir Isaac Newton gave us a whole bunch of the maths and the science that enabled spaceflight to take place. Okay, the first big bit of knowledge he gave us was all of his work about gravity. Okay, he gave us Newton's universal law of gravitation. It's what gives us F equals ma. The force equals mass times acceleration. You may have seen this in physics. Okay, you can see there that the m's are going to cancel out. So I'm using the m of the ma is going to cancel with the m2, like the mass of the planet, if you like. Okay, or the mass of the space station, if you like. And so that formula boils down and drops out to be that the gravitational acceleration is equal to big G multiplied by the mass of the object divided by radius squared, the distance squared between the center of the thing that you're orbiting and how far you are from it. Okay, my second question to you is, can you check this formula, please, to show, using these numbers here, that Earth's gravitational force on its surface is approximately 9.8. Now, there is a little bit of a sting in the tail here, because the radius of the Earth needs to be in meters, and I've given it to you in miles. So your first step is going to be to convert that figure in miles into meters, please. In fact, I'll even do that for you. There you go. Can you stop the video again and just double check? You should get a figure of about 9.8 here. And if that went well, we can continue. So here's a picture of the Apollo Command and Service Module as it orbited the moon with Buzz Aldrin and Neil Armstrong way back in 1969. So your next question. Having got used to this formula now, I want you to work out, why is it that Neil Armstrong bounced on the moon? Use these figures, the ones that you've got on the screen. These are figures from the moon now. Okay, and I want you to compare them to the figure of 9.8 meters per second squared for Earth's gravitational force. And once you've got your figure here for the moon, compare it to that and try to give me a sentence as to why Neil Armstrong bounced on the moon. I'll do that first maths bit for you again, so that radius is in meters. There you go. And the reason that he bounced on the moon is because the gravitational pull on the moon is only 1.6. That's about 1/6 that of Earth's gravity. So whenever we jumped on the moon, you're probably going to jump about 6 times higher, but the rate at which you accelerate towards the ground will be about 1/6 that of the Earth's gravity. It was dangerous up there. They did fall over, and they were only in spacesuits.
I like to skip along, but me, boy, skip. Or whatever you call it. I can't get my left leg in front of me.
It was almost dangerous. You lose sight of the fact that it's a vacuum out there, and if you spring a leak next to it, you're going to be dead.
Uh-oh.
Look at how this one bounces back up.
Nice soft Navy landing. Yahoo! Ah! Boy, do I like to run up here. I feel like Bugs Bunny. That's neat. And here comes the Boxy twin. You're pretty agile there, Twinkle Toes. I'm going out for the ballet when I get back. You learn another line of work up here. And while you're bouncing around there, you might keep an eye out for a nearby crater. Oh, rat. I've been on my knees twice to get back. John? Yes, sir. You are black from the knees down. No way to avoid it.
So this is the rocket that took them to the moon. This is the Saturn V. It's an absolute monster. You can't see anyone on that picture, so I'll show you the next picture. There's the bottom of that rocket. And this is a photo that I took, stood amongst a group of teachers at the base of that rocket. An Apollo launch looks like this. It's a massive affair.
Launch commit, go.
Precisely inserted onto the right orbit.
Now, I just want to compare what you saw there with the new journey into space, that of SpaceX and Elon Musk. The idea here is that it's a lot more efficient, it's a lot cheaper to use a completely reusable rocket. So this is where Elon Musk comes along and says, what about having the boosters re-land? What about reusing every single part of the spacecraft? And so the SpaceX launchers look something like this.
But the film is a sad thing for she's lived it 10 times or more. She could spit in the eyes of fools if they ask her to focus on sailors fighting in the dance hall. Oh man, look at those cavemen go. It's the freakiest show. Take a look at the low man beating up the wrong guy. Oh man, wonder if you'll ever know was there life on Mars?
Now all that science comes back to this thing here. How's that, might you ask? Well, what about if I do this? Same video, turned this way. It's a momentum thing. The total momentum before is equal to the total momentum afterwards. Mass times velocity before is equal to the total mass times velocity afterwards. So on the launch pad, when the spacecraft is still, the total momentum is zero. There's no velocity anywhere. So both parts of that equation are zero. As the thing launches, as any spacecraft launches, you've got a mass times a velocity upwards that's matched by and equal to the mass times velocity of the rocket propellant coming out downwards. Okay. Now at the beginning there, the mass of the spacecraft is huge and it's going very slowly, and that's equal to the mass of the propellant, which is relatively big as well, but going really, really quickly. That reaction there, and it's the same reaction as when you let go of a balloon, that's what pushes the rocket upwards. Okay, and it carries on as it launches up into space even higher and higher and higher. The mass times velocity all the way up is always equal to each other, in terms of size at least. But what happens here is as we use more and more of the rocket propellant, then the mass of the vehicle becomes lighter and lighter. And so it accelerates more and more and more, and that velocity upwards becomes bigger and bigger and bigger until it reaches that magic speed of 17,500 miles an hour, which is enough for it to stay up in orbit. Okay, at A level, that looks something like this. And so here's a question for you. Using that same idea, this is the sort of thing we do at A level. So can you pause the video and have a go at this question, please? And the answer for that is the total momentum before the collision was a mass of 3 with a velocity of 20 plus a mass of 7 with a velocity of 10. That gives you a total momentum of 130. Now that's equal to, well, afterwards, the momentum is 3 plus 7, because two particles join together, multiplied by the velocity, and that's the unknown bit. But what we can do is we can set that 10v equal to 130. So 10v is 130, so the velocity afterwards must be 13 meters per second. Well, as we've already seen, another aspect to spaceflight is this idea of force equals mass times acceleration. And the easiest way to get your head around that is to imagine that if you were the Hulk of these two vehicles that you can see here, which one's going to be the easier one to push? Is it going to be the Mini because the mass is small, so you've got a big force divided by a small mass, which gives you a good deal of acceleration? Or is it going to be the big lorry, which has got a huge mass? So even though you've got a big force, because you're the Hulk, you're dividing by a big mass, and so that's going to give you a lesser or a smaller acceleration. Again, you might think, what's that going to do with spaceflight? And again, all we do is, let's turn it around that way. Which one's the easier one to launch? And as we can see here, at the bottom here, because our mass of the spacecraft is pretty big, the acceleration is fairly slow. As we go up there, we've used up more of the rocket propellant, so the mass is smaller, and so the acceleration is quicker. At A level, that looks like questions like this. Can you pause the video and have a go at this one, please? You're trying to find the acceleration of the car this time using F equals ma. And your answer is your net force here. We've got a driving force of 3,000, but we're also subtracting 600 for the resistive force. That gives you a total or a net force of 2,400 newtons. Force equals mass times acceleration. So that 2,400 is equal to, we had a mass of 1,200 times the acceleration. So the acceleration here, the car must be accelerating at 2 meters per second. Ooh, mistake on the screen, per second. So something completely different now. What about distance to Mars? Mars orbits at that distance from the Sun, that many miles from the Sun. Earth orbits at less miles from the Sun. They orbit at different speeds though, so sometimes they're close together and sometimes they're far apart. My question is going to be, what are the closest and farthest distances that they could be apart? If you're puzzled by that, you might want to have a look at the next diagram. So you've got Earth rotating quicker and Mars rotating slower. Sometimes Earth comes between Mars and the Sun. At another time, Earth will be on the other side of the Sun to Mars. So your answers are, when they're furthest apart, you're just going to add those numbers together. When they're close together, you're going to subtract them. So you're finding the sum and the difference of those two things. A more interesting question is this. At its closest, how many times bigger does Mars appear in the sky relative to its size when smallest? So that means if you look through a telescope when it's smallest compared to when it's biggest, how many times bigger is it going to appear? And the answer is, you take that furthest distance, divide it by the closest distance, and it turns out to be, it's around about 5 times bigger when it's closest to us compared to when it's furthest from us. And finally, from Tim Peake then, our classic question, and I thought you'd ask it, how do you use the toilet in space?
And of course the answer to the big question that everybody asks, how do you go to the loo in space? It really is quite simple. Here's the tube you pee in, take the cap off, turn on the fan, and the airflow keeps everything going down the pipe, and also, for number 2, the airflow does the same thing. Simple as that.
If you've enjoyed this talk and you would like some more space questions, then please take a look at my website at that URL there. And of course, if you enjoy maths and if you like all things science, you are very welcome to come and have a look around the St. Isaac Newton Sixth Form in Norwich. We would love to see budding astronauts there in the future. Thank you very much.